So if I ask you right now, like sitting wherever you are listening to this, whether a number squared is always bigger than the number itself, what does your brain actually do?
Yeah, be honest.
Right, be honest. Because if you're like me, your brain instantly grabs the nearest, friendliest number it can find. We pick 2. 2 squared is 4. 4 is bigger than 2.
Exactly.
And you just think, yeah, absolutely. You lock in your answer, you move on. And in that split second, you have just failed one of the most elite standardized tests in the world.
It's so true.
Because, you forgot about fractions. You forgot about that weird little space between 0 and 1 where 1 high squared actually shrinks to 1/4.
Yeah, it gets smaller,
Mm.
which just breaks our intuition completely.
Right. So today we are completely tearing down the psychological minefield that is the modern computerized adaptive test, like specifically the rigorous graduate management assessments. We are looking at the exact blueprint of how elite tests are engineered to basically use your own brain's autopilot against you.
And I think it's a really brutal realization for a lot of high achievers because, when you sit down at that screen, the clock is ticking, the pressure is immense.
Oh, yeah. Sweaty palms.
Exactly. And the test writers know that under pressure, human beings, we just revert to our earliest, most deeply ingrained cognitive habits.
Like counting on our fingers?
Literally. They know you want to use the counting numbers you learned in kindergarten. They know you want to solve an algebra problem exactly the way your middle school math teacher taught you to, solve for X.
Right.
And they have placed these massive sinkholes, which we're going to call traps today, on the exact spots where your mental autopilot wants to step.
That is just the perfect way to frame it. So for you listening, we're going completely under the hood today in this deep dive. Forget rote memorization. We're taking a stack of incredibly rigorous analytical breakdowns of this exam, and we're extracting the actual machinery.
Yeah, the real mechanics.
Exactly. You won't even need to pick up a textbook after this because we are going to walk through the underlying philosophy of the most common, most destructive traps on this exam. But before we get into the math itself, we have to talk about the structure of the battlefield, right?
Oh, absolutely. The paradigm is completely shifted.
Because there's this equal weight rule on the modern exam that changes literally everything.
It really does. It changes the entire preparation landscape because historically, these exams were heavily weighted toward traditional quantitative and verbal sections.
Right, math and English.
Yeah, but on the modern iteration of this specific adaptive test, quantitative reasoning, verbal reasoning, and data insights all carry equal weight.
Wow.
Yeah, they each make up exactly 1/3 of your total score.
Which is actually terrifying because data insights, it used to be treated like an appendix.
Yeah, an afterthought.
Right. It was that weird section at the end where you looked at a bar chart and tried to muscle your way through some spreadsheet columns. And now, if you treat it as an afterthought, it's a fatal error.
Completely fatal. I mean, data insights is no longer just chart reading. It's this grueling, multi-layered test of executive decision-making.
Okay, what does that actually mean, though?
Well, it requires a complete reasoning architecture of its own. It tests your ability to determine if you even have enough evidence to make a decision in the first place, which is arguably, the most important skill in the modern business world.
It really reminds me of a psychological chess match. Like, the grandmasters on the other side of the screen, the test writers, they aren't just testing your math skills.
No.
They are testing your behavioral impulses. They know the exact square you're going to move your knight to when you feel rushed, and they have placed a landmine right there.
Beautiful analogy, yeah.
So to beat them at this chess match, you have to understand the board. And the atoms that make up this entire universe, like the very foundation we have to start with, are number properties.
Number properties, yeah. This is the primary vehicle for what the item writers call the edge case domain.
Okay, edge case domain. I love that.
It's the core of their strategy. They design mathematical prompts that are completely undeniably true for positive integers.
The counting numbers.
Right. And because our human brains are fundamentally biased toward those positive integers, the 1, 2, 3, 4 of daily life, we fall for it.
We take the bait.
Every time.
Yeah.
But these prompts are engineered to structurally collapse the moment they are exposed to the edge cases.
Meaning 0, negative numbers, fractions, that kind of thing.
Exactly. 0, negatives, proper fractions, and irrationals. The blind spots.
Okay, let's put this into practice immediately so you listening can feel what this trap actually feels like. Let's look at the even-odd logic trap. This is a classic.
Oh, this is a great one.
You're staring at the screen, and the prompt says, if x squared is x even?
Seems simple enough.
Right. Now, I'll be honest. Even knowing this is a trap, My brain instantly builds a mental sandbox and starts playing with blocks. I test x equals 2. 2 squared is 4, which is even.
Yeah, condition met.
Or I test x equals 4. 4 squared is 16, which is also even. So my autopilot just screams, yes, the pattern holds. X must be even.
And that is exactly where they wanted you to go. Autopilot fails because you assumed a mathematical constraint that the prompt never actually provided.
Wait, what do you mean it said x squared is even?
It did.
Yeah.
But did the prompt explicitly state that x was an integer?
Oh, no, it just said x, just the letter.
Exactly. And this is the crux of the edge case trap.
Yeah.
Because it didn't constrain x to be an integer, x could be literally anything in the real number system.
Okay, I see where this is going.
So what if x is the square root of 2? Let's test it. If x is the square root of 2, what is x squared?
Well, the square root of 2 times the square root of 2 is, it's exactly 2.
And is 2 an even number?
Yes, 2 is even. So the premise of the prompt totally holds true. The condition is met.
Right. But look at the question being asked.
Right.
Is x itself even? We defined x as the square root of 2. Is the square root of 2 an even number?
Absolutely not. It's an irrational number. It's like 1.414 going on forever.
That guy.
It doesn't even have a parity. Like, it is neither even nor odd. Oh, wow.
Yeah, by failing to test outside that cozy realm of positive integers, you just walked right into a definitively incorrect assumption. The answer is not yes, because x could be the square root of 2.
That is so sinister. You are effectively penalizing me for having a normal human brain that thinks in whole objects.
That's the game.
And I see how this plays out with positives and negatives, too. Let's look at the inequality trap, because this one gets me every time.
Go for it.
So the prompt asks, if x is less than y, is x squared less than y squared?
A very standard setup.
Again, I'm under pressure. I have 2 minutes. My brain goes to positive integers. 2 is less than 3. I square them both. 4 is less than 9. The relationship holds. So I confidently answer yes.
But think about the geometry of a number line for a second. When you square a negative number, what happens?
It becomes positive.
Right. Squaring essentially takes the entire negative half of the number line and violently folds it over onto the positive half.
That's a great visual.
So if we want to test the integrity of this prompt, we must visualize that negative space. Let's try setting x to -5 and y to -2.
Okay, let's walk through that physically. -5 is further to the left on the number line than -2. So -5 is strictly less than -2.
Right, so that perfectly satisfies the opening condition.
Yeah.
X is less than y.
Okay, now I square them. Because they are both negative, the one that was further to the left, the technically smaller number, actually has a larger absolute magnitude.
Yes, exactly.
Right, so -5 squared becomes a positive 25, and -2 squared becomes a positive 4.
And now evaluate the actual question.
Is 25 less than 4? No, it is absolutely not. The entire relationship just inverted.
Just by stepping across the zero threshold, the mathematical law flipped upside down.
That is wild.
And the behavioral pattern of numbers, it flips when you cross zero, right? But it flips again when you enter the realm of proper fractions, which is another massive blind spot. We actually started the deep dive with this one.
Yes, the is x cubed less than x squared prompt. Let's really dissect why this one is so dangerous. Because the autopilot candidate, they might have studied just enough to know they should test negatives.
A little knowledge is a dangerous thing.
Exactly. So they test positive 2. 2 cubed is 8. 2 squared is 4. 8 is not less than 4. Result is false. Then they feel very clever, and they test a negative number like -2.
They are hunting for the edge case, but they're still trapped. They're still restricted to integers.
Right, so they test -2. -2 cubed is -8. -2 squared is positive 4. -8 is less than 4, so that yields a true.
Right.
They look at their scratch pad. They have a false and a true, so they think they've fully mapped the behavior of the equation. They think the rule is, positives do this, negatives do that.
But they completely ignore the funhouse mirror, that space between 0 and 1. Proper fractions behave in a way that violates our macroscopic intuition.
Because when you multiply 2 whole numbers together, the result grows.
Yes, but when you multiply 2 proper fractions together, the result shrinks. You are taking a fraction of a fraction. So if x is 1/2, what happens?
Let's do it. 1/2 squared is 1/2 times 1/2, which is 1/4.
Okay.
And 1/2 cubed is 1/2 times 1/2 times 1/2, which is 1/8.
And 1/8 is smaller than 1/4. Even though the exponent is larger, 3 instead of 2, the actual value shrunk.
Wow.
The behavioral pattern completely flips yet again in this domain. And if you only test integers, even negative integers, you will never see this reality.
So the overarching lesson for number properties on this exam is that variables are essentially shapeshifters. When you see an x or a y, you have to actively deploy the full spectrum of edge cases. You need a positive integer, a negative integer, 0, a properly fraction, and sometimes an irrational number.
Exactly. You have to aggressively stress test every prompt.
Okay, so that covers how individual numbers behave wildly depending on their domain. But what about when we look at the structure of numbers themselves, like the structural anatomy?
Right, zooming in.
The analysis we're looking at talks extensively about prime factorization, and they call it the coordinate system of integers. I love that phrasing. But what does it actually mean in practice?
Well, think of prime numbers as the raw DNA, the fundamental building blocks of all other integers.
Right.
Any integer greater than 1 can be uniquely broken down into a specific combination of primes. It's like a chemical formula. Water is always H2O, right?
Right.
Well, the number 12 is always 2 2s and 1 3. When the exam asks you complex questions about divisibility or the greatest common factor or the least common multiple of these massive numbers, they are not asking you to do long divisions.
That would take way too long.
Way too long. They are asking you to compare the blueprints. They want you to compare the exponents of these prime factors.
Okay, let's do a detailed walkthrough of this, because I know from experience that if you try to find a greatest common factor by just, listing out factors on your scratch pad, the adaptive clock will brutally punish you.
It will crush you.
The rule for this is elegant, but it requires discipline. The rule is, to find the greatest common factor, the GCF, you take the smaller exponent of each prime shared between the number.
Right, the smaller exponent.
And to find the least common multiple, the LCM, you take the larger exponent of every prime present.
Let's ground this in a real example so the listener doesn't have to hold these abstract rules in their head.
Yeah.
Let's take two seemingly messy numbers, say 540 and 756.
Okay, if I have 2 minutes and I need the GCF and LCM of 540 and 756, brute force is totally impossible. I have to translate them into that prime coordinate system.
Break them down to their DNA.
Exactly. I'll take 540 first. It ends in 0. So physically, I can break off a 10. That's 54 times 10.
Good.
The 10 breaks down into the primes 2 and 5. That 54 is 6 times 9. The 6 breaks down to 2 and 3. The 9 is 3 times 3.
You're doing great.
So if I sweep all those raw blocks into a pile and just count them, I have 2 2s, 3 3s, and 1 5. So the prime blueprint of 540 is 2 squared times 3 cubed times 5.
Perfect. You've stripped it down to the studs. Now for 756, let's break it down methodically. It's an even number, so we can split it by 2. That leaves 378.
Okay.
Still even, so pull out another 2, and we're left with a 189.
Now 189, if I add the digits, 1 plus 8 plus 9 is 18. 18 is divisible by 9, so I know 189 is divisible by 9, and 9 is 2 3s. So if I divide 189 by 9, I get 21, and 21 is just 3 times 7.
Great, so gather up all those primes. You pulled out 2 2s, you pulled out a 9, which is 2 3s, and the 21 gave you another 3, so that's 3 3s total.
Right.
And you have a 7. So the blueprint for 756 is 2 squared times 3 cubed times 7.
Let me write these blueprints side by side so you listening can visualize them. Number A, 540, is 2 to the power of 2 times 3 to the power of 3 times 5.
Okay.
And number B, 756, is 2 to the power of 2 times 3 to the power of 3 times 7.
Now apply the rule for the greatest common factor. Conceptually, the GCF is the largest identical building block that fits perfectly inside both numbers, right?
Right.
So we look at the overlap. We take the minimum exponent for each prime they share.
Okay, so both numbers have a 2 squared. So our shared block has a 2 squared. Both numbers have a 3 cubed. So our shared block has a 3 cubed. Number A has a 5, but number B doesn't.
Right.
Number B has a 7, but number A doesn't. So they don't share the 5 or the 7. We leave them out completely.
Exactly. The minimum shared exponent for 5 and 7 is essentially 0. So your greatest common factor is just the shared DNA, which is 2 squared times 3 cubed. That's 4 times 27.
Which is 108. The largest number that divides perfectly into both 540 and 756 is 108. And we found it without ever doing long division.
Beautiful. Right.
It is. But what about the least common multiple? That's the smallest container that can hold both numbers simultaneously.
Right. So to build a container that can hold either number A or number B, we need to cover all possible bases. We take the maximum exponent of every prime present across either blueprint.
Make sure everyone fits.
Exactly. We need the 2 squared to satisfy both. We need the 3 cubed to satisfy both. But we also must include the 5 to ensure number A can fit inside, and we must include the 7 to ensure number b can fit inside.
So we multiply all the maximal pieces together. 2 squared times 3 cubed times 5 times 7. That's 4 times 27 times 5 times 7, which yields a massive LCM of 3,780.
See, by understanding the coordinate system of primes, you turn an impossible arithmetic chore into a really simple comparison of exponents.
It is incredibly powerful. But of course, because this is an engineered psychological minefield, even within prime numbers, there is a trap. I like to call it the universal destroyer.
Yes, the number 2.
It shows up constantly, especially in the data sufficiency section. You will get a prompt that says something super simple like, if p is a prime number, is p odd?
And the mental autopilot, desperate to save time, just screams, yes, primes are odd. 3, 5, 7, 11, 13, 17, they are all odd.
But the number 2 is the only even prime number in existence. The test writers know that under stress, your brain categorizes prime and odd in the exact same mental folder. They use the number 2 as a structural wedge to just shatter your assumptions. If you forget that 2 is prime, you will confidently mark the question wrong, thinking you just scored an easy point.
It's devastating. And actually, this is a perfect transition because we now see how the static properties of individual numbers can behave unpredictably. But the exam rarely tests numbers in isolation.
Right, they like things moving.
Exactly.
Yeah.
How does the exam test numbers as they interact in dynamic repeating sequences? That brings us to the world of division, remainders, and modular cycles.
This is one of my favorite paradigm shifts from the source material. When you're a kid, a remainder is just the leftover junk math at the end of a long division problem. It's just the pieces that didn't fit.
The scraps.
Right, the scraps. But the analytical breakdown makes it very clear. On this exam, a remainder is not leftovers. A remainder is a coordinate. It records a specific position in a repeating cycle.
This requires a really profound shift in perspective. Think about a clock or the days of the week.
Okay.
If I tell you today is Tuesday, and I ask you what day of the week it will be exactly 10 days from now, you do not sit there and count 10 days on your fingers.
No, I'd look ridiculous.
You know there are 7 days in a week. The cycle length is 7. You divide the 10 days by 7, which gives you one full cycle with a remainder of 3. You just move 3 days forward from Tuesday, Wednesday, Thursday, Friday. The remainder 3 was the exact coordinate of your answer.
Okay, I love that. And to utilize this coordinate system on the exam, you have to adopt a rigid equation translation. When you read a word problem that says integer n leaves a remainder of r when divided by d, you cannot just start plugging in random number.
No, definitely not.
You must immediately translate that English prose into that algebraic formula, n equals d times q plus r.
Let's state that formula really clearly for the listener.
Yeah.
N equals d times q plus r, where n is your starting number, d is your divisor, q is your integer quotient, and r is your remainder.
Got it.
And critically, the remainder r must always be greater than or equal to 0, but strictly less than the divisor d. You write that formula down on your pad before you even touch a calculator.
Let's show why that discipline is required with a classic modular cycle walkthrough. Because these problems look utterly terrifying at first glance.
Oh, they look impossible.
Here is the setup. What is the remainder when 7 to the power of 103 is divided by 10?
Just brutal.
Okay, I'm going to admit, if I see 7 to the power of 103 on a screen, my heart rate spikes. I don't have a calculator big enough for that. The on-screen calculator would just give up and display an error.
And that is exactly the emotional response the test writers are hoping for. Panic. But they do not want you to calculate it. The exam is testing whether you recognize the modular cycle.
Right.
Let's break down the mechanics. When you divide any integer by 10, what is the remainder?
Well, if I divide 42 by 10, it's 4 with a remainder of 2. If I divide 137 by 10, it's 13 with a remainder of 7. The remainder is always simply the very last digit, the units digit.
Exactly. So the terrifying question, what is the remainder when 7 to the power of 103 is divided by 10, is really just a disguised way of asking, what is the units digit of 7 to the power of 103?
Okay, that feels slightly more manageable, but it's still 7 multiplied by itself 103 times.
So we map the cycle. Let's look at the powers of 7 and focus only on the units digit. 7 to the power of 1 is 7. The units digit is 7.
Okay.
7 squared is 49. The units digit is 9. 7 cubed is 49 times 7, which is 343. The units digit is 3. 7 to the power of 4 is 343 times 7. Well, 3 times 7 is 21, so it ends in 1.
Let me track that sequence. 7, 9, 3, 1.
Now, what happens with 7 to the power of 5? We multiply by 7 again. The last digit was 1. 1 times 7 is 7. The cycle restarts. 7 to the power of 6 ends in 9. 7 to the power of 7 ends in 3. 7 to the power of 8 ends in 1. The units Digits for the powers of 7 repeat in a strict, unyielding pattern of 4, 7, 9, 3, 1, over and over again indefinitely.
Okay, so the cycle length is exactly 4. This is just like the days of the week, but instead of 7-day week, we have a 4-day week. We just need to find exactly where the 103rd power lands in that repeating 4-day cycle.
Precisely. So we take the exponent, our target of 103, and we divide it by the cycle length, which is 4.
Well, 100 is perfectly divisible by 4. It's 25. So 103 divided by 4 gives us 25 full cycles with a remainder of 3.
That remainder of 3 is your coordinate. It tells you exactly where to look. It means that after 25 full cycles, you land on the third value in your sequence.
Looking at our sequence, 7, 9, 3, 1, the first value is 7, the second is 9, the third value is 3. Therefore, the unit's digit of 7 to the power of 103 is 3, which means the remainder when divided by 10 is 3.
Yeah.
We just solved a massive computational problem with simple counting logic.
The logic is completely airtight, but we must identify the psychological trap buried at the very end of this process.
Always a trap.
Always. The exam writers know you are under time pressure. A candidate does all this beautiful structural math correctly. They find the remainder of the exponent division is 3. But in their rush to the multiple choice options, their eyes land on the number 4, which was the length of the cycle, and they accidentally select 4 as their answer.
Oh, that is brutal. You did all the work, but you forgot what the numbers represented on your page.
Yes, you have to maintain absolute clarity on your scratch pad about what your numbers represent. Are you holding the cycle length? Are you holding the coordinate? Or are you holding the actual final value? Mixing those up is a devastating unforced error.
Which brings up a great point about keeping your information categorized. The analytical breakdown highlights another tool for this: parity and sign, checking whether an expression will yield an even or odd result or a positive or negative result without actually doing the math.
I consider parity and sign to be low information classifications with incredibly high elimination power.
What does that mean practically?
Think about it in a business context. You're evaluating a massive spreadsheet of quarterly projections. You don't always need to calculate the exact fractional profit margin to the third decimal place to make a decision, right?
No, sometimes you just need to know if the final number is going to be red or black.
Exactly. On this exam, structurally determining the parity or the sign of an algebraic expression can instantly settle a question or eliminate 3 wrong answers before magnitude even matters.
Let's do a walkthrough of that because this saves so much time. Here is a prompt. If n is an odd integer, what is the parity of the expression n squared plus 3n plus 4? Will it be even or odd?
So the autopilot instinct, the one that wants to feel busy, is to pick a number. A candidate will say, okay, n is odd, let's make n equal to 3. Then they grind through the arithmetic. 3 squared is 9, 3 times 3 is 9, 9 plus 9 is 18, 18 plus 4 is 22, 22 is an even number.
Which works. The answer is even. But I can totally see the danger. It took time, and if they picked a larger number like 7 or 9, or if the equation was way more complex, they risk making a silly addition error under pressure. What is the structural logic approach?
We evaluate the expression piece by piece, using only the laws of parity. We know n is odd. First term is n squared. An odd number times an odd number is always an odd number, so the first term is strictly odd.
Second term is 3n. 3 is an odd number. N is an odd number. Odd times odd is odd. So the second term is also strictly odd.
Now we add them together. We have an odd term plus an odd term. Think of physical objects. If you add 3 blocks to 5 blocks, you get 8 blocks. An odd plus an odd always pairs up to create an even number. So the expression n squared plus 3n is strictly even.
Finally, we have the last term, the constant 4. 4 is even. We are taking an even result and adding an even 4. An even plus an even is always even. We didn't calculate 22, we didn't do any heavy arithmetic at all, we just traced the flow of the logic, and the answer is definitively structurally even.
This is the kind of ruthless efficiency the adaptive clock demands. If you save 45 seconds here by using structural logic instead of arithmetic brute force, you have 45 more seconds for a grueling multi-tab data insights prompt later. You are building a time buffer.
Okay, we have mastered the building blocks. We've conquered the edge cases of numbers, the primes, the modular cycles, and parity. But the exam loves to hide these exact same properties behind letters and variables.
It does.
So we are moving from arithmetic into algebra, and our analysis warns that this is where the procedural traps are waiting for you to go on absolute autopilot.
Algebra items are fascinating from a psychological standpoint. They exploit the execution habits that have been drilled into you since middle school.
Like solving for x.
Exactly.
Yeah.
You have been trained for a decade that when you see a variable, your primary unquestionable directive is to solve for x. You want to isolate the letter. The test writers know this, and they create procedural illusions explicitly to punish that exact habit.
The combo trap in linear systems is the absolute best example of this. I want to walk through this slowly because visualizing it changes how you see algebra forever.
Let's do it.
Imagine this scenario. A venue sells adult tickets for $18 and student tickets for $11. In one night, they sold 70 tickets total for a total revenue of $1,050. The question asks, how many adult tickets were sold?
Okay, so we have a classic system of linear equations. Let's define the variables. Let's say A is for the number of adult tickets, S is for the number of student tickets. Equation 1, the ticket count, is A plus S equals 70. Equation 2, the revenue, is 18A plus 11s equals 1050.
Now, what does the candidate on autopilot do? They see two variables, two equations. Their middle school brain kicks in, and they think, I must isolate a variable using substitution.
Right, they can't help it.
They take the simple equation, A plus S equals 70, and they rewrite it as S equals 70 minus A.
Mechanically legal, but strategically disastrous.
Exactly, because now they take that expression, the 70 minus A, and they physically plug it into the massive revenue equation. It becomes 18A plus 11 times the quantity 70 minus A equals 1050.
And now the mess begins.
Right, now they have to distribute the 11. What is 11 times 70? It's 770. So 18A plus 770 minus 11A equals 1050. Then they combine the A's. 7A plus 770 equals 1050. Then they subtract 770 from 1050, which is 280. Finally, they divide 280 by 7 to get A equals 40.
They got the right answer. 40 adult tickets. But look at the cost.
So much time.
They had to multiply 11 by 70. They had to execute a 3-digit subtraction with carrying. They invited 3 different opportunities for arithmetic errors, and they burned 2.5 minutes of precious clock time.
So what is the structural bypass? How do we beat the combo trap?
The exam rewards candidates who recognize structural combination over substitution, the method of elimination. We want to find A, which means we need to mathematically assassinate S. We want to make IDs disappear.
Look at the two equations again. We have one stack of physical tickets that says A plus S equals 70, and we have a financial stack that says 18A plus 11s equals 1050.
In the financial stack, we have 11s. In the ticket stack, we only have a single S. If we mathematically scale up the entire ticket stack by a factor of 11, what happens?
We multiply everything by 11. The equation A plus S equals 70 becomes 11A plus 11s equals 77.
Now literally stack them vertically on your scratch pad, put the heavy financial equation on top, 18A plus 11s equals 1050, and put our scaled up ticket equation directly underneath it. 11A plus 11s equals 770. Now draw a line and subtract the bottom from the top straight down.
Oh, this is beautiful. 18A minus 11A leaves 7A. The 11s minus 11s is 0. It cancels out completely. The S is dead. And 1050 minus 11A is 280. We're instantly left with 7A equals 280. Divide by 7 and A equals 40. We sold 40 adult tickets. It is clean, vertical math, no messy distributions, no massive numbers to carry.
Now a listener might be thinking, I'm fast at substitution. I've been doing it that way my whole life. Why risk learning a new elimination approach when the old one works?
I would absolutely push back and ask that. Like, if it ain't broke, why fix it?
Because you are not just fighting the math, you are fighting the adaptive clock. The clock brutally punishes inefficiency. If you take the long road of substitution, you might win the battle and get the question right, but you paid for it with 60 seconds you will desperately need later in the exam. You are winning the battle, but slowly losing the war.
Wow.
The test writers designed the coefficients, the 18, the 11, the 70, specifically so that elimination works cleanly. It is the intended path.
That is a crucial insight. The test literally wants you to use elimination. Let's talk about another algebra trap that absolutely blew my mind because it's a scenario where algebraic procedure actually violates mathematical law. I'm talking about quadratic extraneous roots.
This is one of the most elegant traps on the entire exam. Let's set the stage for the listener.
You are looking at the screen, and the prompt asks you to solve for x. The equation is the square root of the quantity x plus 5 equals x minus 1.
So square root of x plus 5 equals x minus 1. Step 1 for 99% of candidates is to get rid of that radical sign. They want to free the x, so they square both sides.
Mechanically, it makes perfect sense. It's what we were taught to do. You square the left side, the radical disappears, leaving you with x plus 5. You square the right side, the quantity x minus 1 squared, and you expand that out to x squared minus 2x plus 1.
So now you have x plus 5 equals x squared minus 2x plus 1.
Right. You move everything to one side to create a standard quadratic equation set to 0. You subtract x, you subtract 5. You are left with x squared minus 3x minus 4 equals 0. You factor it into x minus 4 times x plus 1 equals 0. This gives you two perfectly clean roots, x equals 4 and x equals negative 1.
And then you look down at the multiple choice options. And there it is. Option C is a set containing negative 1 and 4. The candidate clicks it, feels a huge surge of dopamine because they successfully executed a multi-step algebraic process, and they move on, feeling invincible.
But the analysis here is devastating. They got it wrong. Why?
Because the trap lies in the strict mathematical definition of the principal square root function. On this exam, the radical symbol, that checkmark symbol over the x plus 5, specifically means the principal or non-negative square root. It is a mathematical impossibility for a principal square root to yield a negative result.
Wait, really? But what about when we solve x squared equals 9? The answer is x equals 3 or negative 3.
That is true when you're solving for a squared variable. But when the exam provides the radical symbol itself, it is strictly asking for the positive root. The square root of 9 is 3. It is not negative 3.
Okay, so how does that break our algebra problem?
Let's test the roots we found by plugging them back into the original equation. Square root of x plus 5 equals x minus 1. Let's test our first root, x equals 4.
Right side, square root of 4 plus 5 is the square root of 9. The principal square root of 9 is 3. Right side is x minus 1, so 4 minus 1 is 3. 3 equals 3. The root x equals 4 works perfectly.
Now let's test the other root, x equals negative 1.
Left side, square root of negative 1 plus 5 is the square root of 4. The principal square root of 4 is 2. Right side is x minus 1, so negative 1 minus 1 is negative 2.
So you are left with the statement 2 equals negative 2. Does 2 equal negative 2?
Obviously not. It breaks reality.
Exactly. The process of squaring both sides algebraically created a false twin, an extraneous root. By squaring both sides, you essentially created a mirror universe where negatives became positives, and you solved for that universe.
But then when you pull it back to the real world...
Right, when you pull that answer back into the real constraints of the original problem, it shatters. The only valid solution is 4. Autopilot fails here because autopilot assumes that if the mechanical algebraic steps are legal, the final answer must automatically be true.
You cannot trust the procedure blindly. You have to verify against the constraints of the universe you are operating in. Let's look at another place where autopilot blindly breaks the laws of physics. Inequalities. Specifically, the sign flip trap.
Oh, this one is incredibly easy to fall for because, again, it relies on middle school muscle memory. The prompt asks, if a times x is greater than b, is x greater than b divided by a?
Most people look at that inequality symbol, the greater than sign, and their brain just visually translates it into an equal sign. They see times x equals b. They want to isolate x, so they divide both sides by a. They get x equals b over a. So when they look at a times x is greater than b, they divide both sides by a, get x is greater than b over a, and confidently answer yes.
But our analysis stresses a fundamental law. You can never, ever divide an inequality by a variable unless you definitively know the sign of that variable.
Why is that? What physically happens?
Think about the number line again. If a is a positive number, multiplying or dividing by it maintains your orientation on the number line. The inequality is preserved. 2 is less than 3. Multiply both by a positive 2, and 4 is less than 6. It holds.
Okay, that makes sense.
But if a is a negative number, multiplying or dividing by it is the equivalent of spinning 180 degrees to face the opposite direction on the number line. Mathematical rules dictate that the inequality sign must physically flip to remain true.
So if a is a negative variable, dividing a times x is greater than b by a actually results in x is less than b over a.
Precisely. Because the problem, if x is greater than b, is x greater than b over a, never specified whether a was positive or negative, you cannot execute the division. You lack the structural clearance to make that move.
Wow.
The answer is not yes. It is that you do not have enough information to know. The distractor option perfectly targets your failure to establish the sign before operating.
It all comes back to constraints. And speaking of constraints, there is one mathematical concept that is entirely defined by spatial constraints, and it is heavily tested: absolute value.
Absolute value is deeply misunderstood. The core concept here is that absolute value isn't just a magical set of parallel lines that makes negative things positive. Absolute value is a literal measure of physical distance on the number line. It is the distance a number is from 0.
And distance cannot be negative. You cannot walk negative 2 miles to the grocery store.
Right. And when dealing with inequalities, you have to understand spatial boundaries. Strict inequalities, like less than or greater than, exclude the endpoints. They are open borders.
Let's walk through a classic bounds problem. The absolute value of 3x minus 6 is strictly less than 9. Written out, that's vertical bar, 3x minus 6, vertical bar less than 9. How do we structurally dismantle this without making an error?
Because it's a less than inequality, it is measuring a contained distance. The distance of the entity 3x minus 6 from 0 is less than 9 units. This means the entity is trapped in a spatial corridor. We must carefully open it up into a compound inequality. The internal expression must exist somewhere between -9 and +9. So you write it out immediately as a three-part chain. -9 is less than 3x minus 6 is less than 9.
Now we have a physical corridor, and we solve it globally all at once. We want to isolate x in the middle. First, we add 6 to all three sectors to get rid of the -6. Left side, -9 plus 6 is -3. Middle, 3x minus 6 plus 6 is just 3x. Right side, 9 plus 6 is 15. So our new corridor is -3 is less than 3x is less than 15.
Now divide every sector by a +3. Left side becomes -1. Middle becomes x. Right side becomes 5.
So our final spatial boundary is -1 is less than x is less than 5. We just mapped the exact interval where x is allowed to exist. That feels very controlled and safe.
It is safe if you respect the geometry. But here's the trap they will set for you. What if the prompt asks you to solve this equation? The absolute value of x minus 3 is equal to -2.
Oh, the autopilot is so trained to execute the splitting procedure. The brain says, okay, absolute value equations get split into two. They split it into a positive and negative version. Version 1 is x minus 3 equals -2, which yields x equals 1. Version 2 is x minus 3 equals 2, which yields x equals 5. And I guarantee you, the multiple choice options will proudly offer the set containing 1 and 5.
But we must violently stop the autopilot, step back from the algebra, and look at the physical statement you are making. Absolute value is physical distance. The equation literally says the distance between x and 3 is equal to -2.
Which is impossible. As we established, you cannot walk -2 miles.
So an absolute value can never equal a negative number. The correct answer is instantly and definitively no solution. You don't do a single piece of arithmetic. If you blindly execute the algebraic splitting procedure without observing the physical structural impossibility of the premise, you fall straight into the trap.
You have to keep your eyes open to the reality of the structure, not just the symbols. There's one last piece of algebra we should cover before we cross the threshold into data insights, and that is functions and the strategy of using smart numbers.
The best way to understand functions on this exam is to stop thinking of them as abstract math and start thinking of them as physical machines in a factory. A function simply assigns one specific output to each permitted input you feed into it.
The notation trap here is severe. When you see f parentheses g parentheses x, what does your brain want to do? It sees two letters next to each other, f and g, and it assumes multiplication. It wants to multiply machine f by machine g.
Which is a complete misunderstanding of the architecture. F of g of x means composition. It is an assembly line. You take your raw material, x, and you feed it into machine g. Machine G processes it and spits out a product.
Okay.
You then take that newly manufactured product, G of X, and you feed it as the raw material into machine F. You must evaluate from the inside out.
Assembly line logic. I like that. Now, regarding smart numbers, this is a vital strategy when dealing with ratios where the absolute totals aren't as important as the proportional relationships. The exam loves to bury you in messy fractions if you try to solve ratio problems algebraically.
Yes, specifically allocation problems. Let's walk through one.
Imagine a venture capital fund allocates capital to investment X and investment Y in a strict 2-to-5 ratio. The total allocation for both combined is $70 million. The question asks, how much capital exactly goes to investment X?
The trap here is psychological. Candidates get flustered by the word ratio and start doing chaotic math. They treat the ratio parts 2 and 5 as absolute dollar amounts. Or worse, they take the 70 million and divide it by 2, or divide it by 5, trying to find a shortcut.
The smart number scaling method is so clean and physical. Instead of fractions, let's treat the ratio as visible blocks or shares. Investment X gets 2 shares. Investment Y gets 5 shares. Let's call it share K. So X gets 2K and Y gets 5K.
If X gets 2 shares and Y gets 5 shares, how many total shares exist in the entire pool?
2 plus 5 is 7. There are exactly 7K total shares. And we know from the prompt that the total pool is worth 70 million.
So set them equal. 7K equals 70.
Which means the multiplier, the value of a single share K, is exactly 10.
You've unlocked the scale. Now, just answer the question asked. How much goes to investment X?
Investment X was assigned 2 shares, which is 2K. 2 times 10 is 20. Investment X gets 20 million. It completely bypasses the need to set up complex fractional equations like, X equals 2/7 of 70.
Yeah.
It grounds the abstract ratio in physical, countable units.
Okay. We've looked at single formulas, single equations, and isolated logic rules. We've mastered a number of properties in algebra, But what happens when the exam stops giving you neat equations? What happens when there's contradictory data points, multiple tabs of dense reading, and real-world physical constraints at you simultaneously while the clock is ticking down?
That is when you entered the Thunderdome. Welcome to Data Insights. This section is the ultimate integration phase. As we discussed, this is a full third of your score. But it tests a completely different mental muscle. It tests your ability to determine if you have enough information to solve a problem without necessarily asking you to actually do the final calculation.
The data sufficiency format within this section is legendary for its difficulty. It requires a brutally strict, almost robotic decision framework. There are 5 standardized answer options. If you do not have these options memorized and internalized, the cognitive load of rereading them during the test will destroy your pacing. We must meticulously walk through them.
Let's lay them out clearly. Option A, statement 1 alone is sufficient to answer the question, but statement 2 alone is not. Option B, statement 2 alone is sufficient, but statement 1 alone is not. Option C, both statements together are sufficient to answer the question, but neither statement is sufficient independently. Option D, each statement alone is sufficient independently. Option D, even when you combine statement 1 and statement 2 together, you still do not have enough information to answer the question.
To navigate this minefield, there is a golden rule. It is a strict operational protocol you must adhere to avoid psychological contamination. First, you read the main prompt. Then you test statement 1 entirely alone. You assume statement 2 does not exist.
Right.
Once you have determined if statement 1 is sufficient or not, you must actively, consciously erase it from your working memory.
I have to say, that is the hardest part of the entire exam, pretending you didn't just read a vital piece of information.
You must quarantine it. Because step 3 is to test statement 2 entirely alone. You assume statement 1 does not exist. Only if both statements fail independently, only if they both prove insufficient on their own, do you allow yourself to merge them, combine the data, and test them together for option C.
The biggest psychological trap here is cross-contamination. Combining the statements too early. You read the prompt, then you read statement 1, then your eyes naturally drift down, and you read statement 2.
Yet you can't help it.
And they make sense together, they paint a complete picture, and your brain instantly jumps straight to option C. Or you read statement 1 and you realize it is perfectly sufficient. Then you read statement 2, and because it agrees with statement 1, you think, oh, they support each other, so I need both of these, when actually either one would have worked independently, which is option D.
Let's refine this framework further by differentiating between the 2 primary subgenres of data sufficiency questions. Value questions and yes or no questions. They require completely different sufficiency thresholds.
Right. For a value question, for example, the prompt asks, what is the precise value of X? Sufficiency has a very strict, unforgiving definition. It means the statement must lock down exactly one numerical answer. If a statement tells you X could be 4 or it could be 5, it is not sufficient. It must isolate a single point on the number line.
But yes or no questions are much more subtle, and they contain a massive psychological trap. Let's walk through an incredibly important example. The main prompt asks, is integer n negative? Statement 1 provides this clue. N cubed is less than 0. Statement 2 provides this clue. N is non-zero.
Okay, following the golden rule protocol, quarantine statement 2, I look only at statement 1. N cubed is less than 0. We talked about parity and signs earlier. If an integer cubed results in a negative number, what does that mean about the base number? Well, a positive times a positive times a positive is positive.
Right.
Only a negative times a negative times a negative yields a negative result. So if n cubed is negative, n itself absolutely must be negative.
So does that answer the main prompt is integer n negative?
Yes. It answers it with a definitive, unshakable whys. Statement 1 gives me enough information to answer the question. Statement 1 is sufficient.
Perfect. Now, execute the protocol. Erase statement 1 from your mind completely. Look only at statement 2. N is non-zero.
Okay, if n is non-zero, it could be positive 5 or it could be negative 5. If it's negative 5, the answer to the prompt is yes. If it's positive 5, the answer to the prompt is no. Statement 2 permits contradictory results. It does not lock down a definitive yes or no. Therefore, it fails. It is not sufficient.
So the final answer would be A. Statement 1 alone is sufficient. Now let me modify this to expose the crucial realization that trips up even advanced, highly prepared candidates. What if the statement definitively proves that the answer to the prompt is NO?
Oh, this is the paradigm shift. Let's say the prompt is integer n negative, but the clue provided in statement 1 is simply n equals 5.
Exactly. Read that. The prompt asks, is n negative?
Right.
Statement 1 says n is 5. Does statement 1 give you enough evidence to answer the question?
Well, yes. If n is 5, then the answer to the question is N negative is definitively 100% NO and is not negative.
Exactly. A definitive NO is sufficient. It is just as efficient as a definitive yes. But psychologically, candidates are wired to seek positive affirmation. They feel that because the answer to the prompt is a negative, no, the statement itself must be flawed or insufficient. Rejecting a consistent no result as insufficient is a massive, carefully engineered psychological trap.
You are evaluating the sufficiency of the evidence. You are not evaluating whether the evidence supports a positive outcome. That really is a mental operating system upgrade. It completely changes how you read the prompts. Let's move to another data insights trap that I find absolutely fascinating because it relies on reading comprehension as much as math. Real context constraints. I like to call these the hidden rules.
The exam writers are brilliant at hiding vital mathematical constraints in plain English words. Words that describe physical reality. Words like crates, people, shipments, or tickets. When you see these words, they carry invisible mathematical baggage that you must unpack.
The walkthrough in our analytical breakdown for this is just a fantastic immersive puzzle. I want to spend some real time on this. Here's the scenario. A shipping company is loading a cargo plane. The shipment uses a collection of identical crates. The total mass of the shipment is exactly 2,500 kilograms. We know that each individual crate weighs more than 95 kilograms, but less than 105 kilograms. What is the exact number of crates in the shipment?
Okay, let's feel the pressure of the clock. We have a total mass, and we have a bounded range for the weight of a single unit. Let's do the bounds math first to establish our physical corridor.
If the total mass is 2,500 kilograms and the absolute maximum possible weight for a crate is just under 105 kilograms, we divide the total by the max weight to find the minimum number of crates. 2,500 divided by 105. That gives us a lower bound of roughly 23.8 crates.
And to find the upper bound, the maximum possible number of crates, we assume they are as light as possible. We divide the total 2,500 by the minimum weight of 95. 2,500 divided by 95 gives us about 26.3 crates.
So mathematically, algebraically, the number of crates in this shipment must be somewhere between 23.8 and 26.3.
Now, a candidate on autopilot looks at that interval, 23.8 to 26.3, and sees an infinite number of decimal possibilities. They think there is no way to lock down a single exact value. I don't have enough information. And they prepare to select insufficient. But what is the first hidden English constraint?
The word crates. A crate is a physical macroscopic object. You cannot ship 0.8 of a wooden crate. You cannot have 24.2 crates. Crates must be positive integers. This invisible rule instantly collapses that infinite decimal range down to just 3 possible physical realities. The crate count must be strictly 24, 25, or 26.
Excellent. We have narrowed the universe down to 3 integers, but the question asks, what is the exact crate count? Implying we must find a single definitive value to achieve sufficiency. How do we eliminate 2 of these 3 options? We need another constraint.
This is where you have to read the prompt like a lawyer. Let's reread the opening sentence carefully. The shipment uses identical crates, each weighing a whole number of kilograms. There it is.
The second hidden constraint. The mass of each individual crate cannot be a decimal. It must be a positive integer.
So we have to test our 3 surviving physical realities, 24, 25, and 26 crates, against a total mass of 2,500 kilograms, and see which one produces an integer weight. Let's test them.
Scenario A, there are 24 crates.
We take the total 2,500 kilograms and divide it equally among 24 crates. 2,500 divided by 24 is 104.16 kilograms per crate. 104.16 is a decimal. It violates the whole number of kilograms constraint. So 24 crates is a physical impossibility.
Scenario B, there are 26 crates.
2,500 kilograms divided by 26 crates. That comes out to 96.15 kilograms per crate. Again, a decimal. It violates the constraint. 26 crates is impossible.
Scenario C, there are exactly 25 crates.
2,500 kilograms divided by 25 crates. That equals exactly 100 kilograms per crate. 100 is a whole number. It satisfies the integer weight constraint, and 100 kilograms is safely between the 95 and 105 limits.
Therefore, the only crate count that satisfies both the physical integer constraint of the objects themselves and the stated integer constraint of their mass is 25. The prompt provided perfect sufficiency. If you ignored the real-world implications of the word crates or skim past the phrase whole number of kilograms, you would have sworn the problem was unsolvable.
It is a masterclass in translating English reality into mathematical boundaries. You cannot treat word problems as just numbers wrapped in useless fluff. The fluff is the structural cage that makes the problem solvable.
Now, in the data insights section, you actually have an on-screen calculator available because the math can get dense. But our analysis is aggressively strict about what they call calculator discipline.
Yeah, you would think having a calculator makes it easier, but it actually introduces a new vector for catastrophic errors.
The calculator is a tool. It is not a crutch, and it is certainly not a structural guide. If you dive straight for the calculator the moment you see numbers, you will lose the logical architecture of the problem and almost certainly fall for an intermediate value trap. The unbreakable rule is estimate first, calculate second, reconcile third.
Let's do an example of how this prevents disaster. Let's say you've set up your equations perfectly, and your final step is to evaluate the fraction 497 divided by 19.
If you start blindly typing 497 divided by 19 under adrenaline, you might miss a keystroke. You might hit 498. You might hit 29 instead of 19. If you just accept whatever number the screen spits out, you are flying blind. We must estimate by benchmarking first. 497 is very close to a beautiful benchmark number 500.
And 19 is very close to 20.
So our benchmark fraction is 500 divided by 20.
Which is just 50 divided by 2. That is exactly 25. So our estimate is 25.
Now look at the proportional adjustments we made. The numerator drops slightly, from 500 down to 497. The denominator also dropped slightly, from 20 down to 19. Because they both dropped, the effects mostly offset each other. We should expect the true exact answer to be very close to 25, perhaps slightly higher, because dropping 1 unit from a small denominator like 20 is a larger percentage shift than dropping 3 units from a massive numerator like 500.
Okay, now that I have that logical anchor, I type 497 divided by 19 into the calculator. The screen spits out 26.157.
Step 3, reconcile. You look at 26.15. You compare it to your logical anchor of slightly higher than 25. They match perfectly. You now know you didn't accidentally hit a wrong key. You have verified your own math. The trap they want you to fall into is entering numbers before writing down the governing relationship on your scratch pad, getting a weird decimal, panicking, and guessing.
This level of discipline is essential when dealing with format recognition, which is another massive component of data insights, specifically the multi-source reasoning prompts, or MSR.
MSR is designed to simulate the chaotic desk of a project manager. The exam will give you 3 separate tabs of dense information. Maybe tab 1 is a messy email chain arguing about a deadline, tab 2 is a spreadsheet of budget allocations, and tab 3 is a dense legalistic policy document. Then it will ask you to evaluate a series of claims based on a synthesis of all 3.
The trap here is that candidates try to flatten a multi-response, multi-source task into their ordinary linear 5-choice habits. They try to read the question first and then just hunt and peck randomly through the tabs looking for keywords.
Which is suicidal for your pacing. The analysis strongly advises indexing each tab by its functional source role before you even look at the questions. You read quickly not to memorize the numbers, but to build a mental map of the architecture. You tell yourself, okay, tab 1 is the timeline, tab 2 is the money, tab 3 is the rule book.
So when the question asks, does the proposed budget for Phase 2 violate the compliance standards, you don't panic. You know exactly where to go. You pull the number from tab 2, the money, and you verify it against tab 3, the rule book. You aren't wasting time scanning the emails in tab 1.
Exactly. You are managing the flow of information rather than letting the information drown you. And to survive that kind of intense time pressure, our sources also provide a list of numerical constants that are worth memorizing. They call them tools, not substitutes for derivation, but having them instantly available in your RAM frees up your working memory for the complex logic.
Yes, the cognitive load theory. If you are using brain power to calculate basic decimals, you have less brain power available to notice the hidden integer crate rule. You should absolutely know your common fraction to decimal pairs cold. 1/8 is 0.125. 1/6 is approximately 0.167. 3/8 is 0.375.
You should also be able to instantly visually recognize all the prime numbers below 30. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. If you see the number 23 in a fraction, your brain should instantly flag it as a prime, meaning it can't be reduced further unless the numerator is a multiple of 23.
It just saves those precious, precious seconds. Every time you have to manually calculate that 1 divided by 8 is 0.125, you are burning cognitive fuel that you desperately need to navigate the actual logic trap of the problem.
So we have covered an immense amount of ground today. What does this all mean for the listener who is staring down the barrel of this exam? We've decoded the machinery, from the fundamental edge cases of the number line to the rigid procedural traps of algebra to the complex logical frameworks of data insights.
It means that the mental operating system replacement is complete. If we quickly recap the major paradigm shifts of this journey, we learn that the number 2 is the universal destroyer of prime assumptions. We discovered that remainders are not leftovers. They are precise coordinates in a repeating modular cycle. We saw how squaring an algebraic equation can create a false twin universe full of extraneous roots. We learned that absolute value is physical distance and that inequalities flip when subjected to negative gravity. And we mapped the rigorous quarantine-level isolation required to accurately evaluate data sufficiency evidence.
I want to leave the listener with a philosophical application of this material, because the true value of this deep dive extends far beyond a standardized test score. This exam is not just testing math. It is an intricate sandbox testing your executive decision-making.
How so? Connect the dots for us.
Think about the real business world you are preparing to enter. When a financial analyst brings you a massive data set or a quarterly projection, do you blindly fall for the edge case trap? Do you assume the data points to infinite positive integer growth when the reality might involve negative constraints, shrinking fractional returns, or irrational market behaviors?
Wow. When you put it like that, the positive integer bias is basically the root cause of every major financial bubble,
Ugh.
assuming the line only goes up and to the right in whole numbers.
Precisely. And when you are presented with competing reports from different departments, say an aggressive sales projection and a conservative manufacturing limit, do you combine those sources of information and blur them together before evaluating their biases independently? Or do you employ the data sufficiency golden rule, isolating each claim, testing it for structural integrity on its own before synthesizing a strategy?
The logical structures that beat this exam, identifying hidden constraints in plain language, demanding definitive sufficiency of evidence before acting, recognizing elegant structural combinations over brute force labor, these are the exact same logical structures needed to navigate a professional environment defined by intense information overload, high stakes, and constant uncertainty.
The exam is simply a compressed, high-speed simulation of reality. The traps they set with X and Y are the exact same traps the market sets with supply and demand.
That is an incredible, profound takeaway. The exam isn't an obstacle, it's a training ground for the real-world skills you absolutely need to survive. Thank you for taking this incredibly rigorous deep dive with us today. For everyone listening, remember that paved, predictable road we talked about at the beginning? It does not exist here, and it doesn't exist in the real world either. But now, you aren't walking blindly. You have the blueprints to the maze. True mastery is seeing the gears of the machinery before the trap even has a chance to disguise itself. Keep analyzing, keep stress testing your assumptions, and keep diving deep.